Welcome once again to A-level physics under topic 2 kinematics, 2.1 equations of motion. Number 8 in the syllabus, describe an experiment to determine the acceleration of free fall using falling object, sketching of graph. Right? We're looking at different graphs, especially parabola and hyperbola. Okay, measuring G. Right? What's the problem of measuring G by yourself using a stopwatch and a ball bearing? Right? You just drop the ball from a height and time the fall. The error due to reaction time is large. It's about 0.2 seconds. This will give a large percentage uncertainty, which will calculate roughly in a while. Error in height is usually negligible because the height can choose 1 meter and the uncertainty is 1 millimeter. Right? Example, dropping a ball, we use the equation of motion S equals to ut plus half at squared, u equals to 0. Right? We drop it, initial speed is 0. So it's half gt squared. That's the equation that we use. So our h is, we can take a height of 1 meter. Uncertainty is 0.001 meter. Time about 0.5. Uncertainty due to reaction time is 0.2. Right? Even though your stopwatch may be able to read to 0.01 second, you still have to take the reaction time because the reaction time gives a greater uncertainty. So from that equation, G cross multiply, take 2 across, take t squared down. So you got 2h over t squared. Right? Put in the value, there's a 2, h is 1, t squared, that's a t squared. Calculate is about 8.0 meter s minus 2. Okay, so calculation. Usually we'll neglect this error because this error is too small. No point in calculating, it won't show up in the calculation. So percentage error in G equals percentage error in H. Right? 2 is a constant, so doesn't have uncertainty. Plus 2, 2 because of that power, 2, so times 2, percentage error in T, error or uncertainty. So this one is negligible, right? Less than 1%, so no point. So this is 2, 0.2 over 0.5, you can see it's very large. This uncertainty is very large, 80%. So we never use this method to determine the value of G. And you can use simple pendulum method. A bob tied to a string and clamp it with 2 pieces of wood. Bob with small displacement of less than 10 degrees as a period given by this equation. L is the length of pendulum. We measure from the point of suspension. There's a point of suspension there, that point, to the center of the bob here. G is the acceleration due to gravity. So that is the equation. The period equals to 2 pi square root L over G. Right? If we square that, we get T squared. Right? It's 4 pi square over G. These are constant. L. Right? We compare the equation of straight line. The y-intercept is 0. So the gradient is just your 4 pi square over G. Right? We plot a graph of T square against L. Right? Determine the time for 20 oscillation. Repeat the timing and record the length and time. Repeat the above for different length. Tabulate length, time, period, and period square. and then plot a graph of t square against L. And we can calculate the gradient, and then the gradient equals to 4 pi square over g. Then you can calculate your g. Or we can use a mechanical method. There's your electromagnet, there's your switch, and then it's connected to a timer. So as the switch is closed, the electromagnet is on, so the steel ball is held by the electromagnet. So when the switch is open, it will cause the timer to start. And the trapdoor acts as another switch. As the ball hits the trapdoor will open, it will cause the timer to stop. Right? To find the acceleration due to gravity, we can use trapdoor and electromagnetic method. This experiment involves dropping a steel ball connected to a timer release, which when broke will start a timer. This is open the switch, it starts the timer. Then once the steel ball hits the trapdoor, the timer will stop because it's a switch. When the switch, the timer will stop. So we have a time lag. The timer can be read to 0.01 second, which is the advantage. Uncertainty is smaller. We can use a different height and plot height against t square. Let's go to the theory. In free fall, we take downwards as positive, u equals 0, a equals to g. And we are interested in time. We're interested as the height of fall or equals to h. So that's our equation of motion. U equals to 0, a equals to g. Put it in there, h over t square. So compare to equation of a straight line. Y equals to mx. This is your gradient. Right? So we measure the time at different height. You can tabulate the height and the time. Then plot a graph of height against t square. So that is your gradient. Right? And because half g equals to 2 times the gradient. Right? Often when we plot a graph, the points are scattered about roughly a straight line. Right? Because of random error. So we draw the best straight line. This is called the line of best fit. Okay, then we can find the uncertainty. Sometimes our line doesn't pass through origin. What's the problem? Shows the presence of systematic error. Example, constant time delay. Right? We have a stopwatch that is not 0, or stopwatch may not start instantly as the ball is dropped. Right? Alternatively, we can take square root of h, square root of h, square root of g over h, and then square root of t squared becomes t. Right? So there's either way we can do that. Root h against t, and then the gradient in this case is g over 2, square root g over 2. Right? There are various gadgets in the market to measuring acceleration due to gravity. Right? Some apparatus use electromagnet to hold and release the ball. When the ball is released, the timer starts. On connected to the timer and stop when the ball hits the contact pad or impact sensor. There's an impact sensor there at the bottom. Right? These are just for info. That these are various apparatus we can use to study motion. This is your ticker timer. There's a trolley. The friction compensator track literally doesn't have friction because you adjust the height so that when the trolley is pushed, it moves with constant velocity. So the hanger and slaughter mass placed there provide different force and thus accelerate this trolley with different acceleration. Right? Or we can use a linear air track. This is our timer. Blower, blow the air inside the linear air track. Right? There's a photo gate. There's a photo gate there. Photo gate air. It's your vehicle or glider. There's a linear air track. This one present to you how the linear air track would look like. There are holes there. Provide a frictionless horizontal surface to study types of motion and collision. The blower provides air. Right? You blow air into the linear track. Air blown in comes out of the hole on the air track. So the vehicle or glider sits on a cushion of air. That's why there's no friction. Before using the air track, of course, you need to adjust so that it's horizontal. Using a spirit level to test for its horizontal. Right? These are various views of linear air track. Particular in linear air track experiment, we want to measure the velocity. So there's a vehicle or glider. That is your photo gate. Right? Photo gate, there's an emitter. Photodiode. Photodiode is the detector. Photogate consists of a source of light. Sorry, some mechanical problem. Okay, back to it. Light from the emitter falls on the detector. So you can think of it as it's a switch. Close the switch. Produce an electrical signal. The change in signal when an object interrupts the beam may be used to trigger a timer. So usually, as an opaque card of length x passes through the photo gate, the time t is recorded by the timer, and the average speed of the vehicle is calculated as x divided by t. There's an x. Right? So as the card enters the photo gate, it will cut the light. So as the light is cut off, the timer will start. And as the card passes, the detector will detect the light again, so the timer will stop. That's how we measure our time. Right? The other one is stroboscopic photograph. Right? Stroboscopic photograph is a rather more abstract branch of photography consisting of a flashing strobe light and a camera with an open shutter. Photographic photos, stroboscopic photos must be taken in darkness so that every time the strobe flashes, A still image is taken of the moving object at the instant, done in a dark room. So if you like, if you are reading it, that is where your camera will be facing that woman that's sitting down there. And you got a stroboscope near the camera flashing at particular frequency. So as soon as the stroboscope light is on, it will capture an image of the two hands that's moving. Right? So these are all at equal time. Okay, so if you're interested how this person did it, you can Google it. A stroboscope is a regular flashing light. The time between flashes can be controlled by a dial on it. Each time the light flashes on, the position of the ball is captured on the camera film. Right? There's a stroboscope. There's your camera. It's all done in a dark room. So instead of 30, the projectile motion, you can drop a ball. You can drop a ball from a height in a dark room. Then we can study about the displacement and time. We plot a graph of S versus T square. Right? That's our equation of motion. And compare. And the gradient becomes half A. Right? A is the acceleration, T is the time. Right? That's what we see. Multi-flash or stroboscopic photograph. That's what we see. Right? Remember the time between the ball are the same. The height is changing. The distance between the ball is changing, is increasing because the velocity is increasing. Or we can study projectile motion. Right? Motion in two dimensions. Projection of ball at an angle. Notice the distance between the ball or image increases downwards. Okay, let's look at the graph. Right? Velocity displacement graph for uniform acceleration. Throwing a ball upwards with a velocity 20 meters per second. So our initial velocity is 20. Our G for sketching, we are not so particular about the value. We have one approximation. G is 10. So our independent variable is S. Our dependent variable is V. Right? We change our different height, measure the velocity. Right? We can throw the ball out. The ball is thrown upwards with the initial velocity. So we are interested in at different height, what's the speed. So that is the equation. V square equals U square plus 2AS. Put in the value. U square 20 square is 400. Right? Minus, because you're throwing up, so you're taking upwards as positive. But G is downwards. G is pointing downwards. Right? Sorry. We are taking upwards as positive. So we have to put a negative sign there because G is pointing downwards. Okay, so that is how the graph looks like, a parabola of V square equals to 400 minus 20, 20 SS is a displacement. It's a hyperbola, 1 over x, y equals 1 over x. Right? That's how a parabola looks like. Y equals to x squared. We can plot a graph, sketching graph. Okay, here is a parabola, the red line, red one. We choose our A as 5. If we choose our K as 80, then it will start at 80. It's just the inverted, that's all. 80 minus 5x squared. So this is your y equals to 5x squared. Is 80 minus 5x squared. We start with 80, then be 0 there. A ball is thrown upwards with a velocity of 20 meters per second. Given u equals to 0, g equals to, sorry, it should be 20. Okay, there's our equation of motion. Choosing upwards as positive, so there should be a negative sign here. We put in our value for 20 here, t minus 10, 10 divided by 2 is 5. So roughly we can sketch the graph. Right? If we don't know how the graph looks like, you can put in value and then roughly use a graph paper to sketch it so that you know how the shape looks like. Right? 0, time is 0 to 4 seconds. Right? This is a parabola. Have your x squared. This is also a parabola, and this is a y squared. Right? That way. But remember, this is not a sharp point. The computer cannot draw it properly for you. It is a smooth curve. Right? Okay, so that's the uniform acceleration. Dropping a ball. You drop a ball, that's how it looks like, the graph. U equals to 0, taking downwards as positive, or it can be a car accelerating from rest. Right? In this case, you are dropping the ball, G is 10, about 10. Variable is S and T. So U equals 0. Substitute in the value, A equals 10. So it's 5T squared. So that's your uniform parabola for uniform acceleration. Right? Displacement time graph. Okay, so that's the end of the lecture. Thank you.